right, mic check. Okay, people on Zoom, can you hear me?
Yeah.
Perfect, thank you. Is the knee brace new? Oh, sorry. Always wondered what this thing was for. I was like calling and, should I call class to order or something like that? Pound on the podium. Looks as though it's actually gotten a decent amount of use, so maybe I don't know. All right, we can go ahead and get started. So a couple things coming up. So today I'm going to do more of a traditional lecture. Going to try to keep things as somewhat consistent, but depending on sort of where we're at and what we need and what I need, we might switch a little bit between sort of traditional lectures like today and the story we've done in the past and somewhere in between. So we'll try to kind of hit on all three of those probably. Questions on anything? Any questions? Homework? Homework questions? Yeah, I can talk about it afterwards if you want. Or is it something you want me to address to everybody, you think? Okay, I'll talk about it afterwards with you. Yeah, there were some questions on the homework. Somebody had asked about if I could make a review sheet for what's going to be kind of on the test for next Friday. So yeah, I'll definitely try to work on that over the weekend and be able to have that to you sometime early next week. I have not forgotten about the request to do video on just like Lewis structures and drawing structures and stuff like that. I haven't forgotten about that. I just haven't got there yet. And I also haven't forgotten about your first homework. That's in my stack of grading to get through. So hopefully I'll get that done this weekend as well. Other things. Any other procedural things before we jump right back in?
Yeah, will quiz or the chapter 3 quiz be posted online this weekend sometime, or?
Yes, yeah, and that'll be due probably the end of Monday is what I was planning for that one. Yep. Thanks for reminding me on that one. Yep, so I'll get that up this weekend, and then that'll be due the end of Monday. Chapter 3 is kind of a long chapter, so give you a little extra time. I think that's pretty much it. So, all right, so we'll jump right into stuff for here. And last class, I felt like we left fairly confused in terms of which way oxygen, when O2 reacts, when OH radical reacts, and how to kind of tell, how to tell when and how. And we'd used some bond energies to be able to predict the different ways, but sometimes that's a little tricky. And it turns out there's actually really helpful flowcharts in the textbook. So a lot of this information can be found in chapter 17 if you're looking. But essentially, if we're asking the question of how, when and how does hydroxy radical react and O2 react, well, we've got two different flowcharts. And the first is when I'm dealing with a neutral species, and that's really a misnomer. I'm sorry, I couldn't think of a better term, because radicals can be neutral too. I'm not talking about it being charged. What I mean is simply that it's not a radical. It's a stable species. It has all of its electrons paired. So if we're dealing with that, then where we start, and you don't have to write this down, I'll make sure that it's posted, and also that it'll be on subsequent slides as well. But the first, our flowchart starts kind of at the top, and we just ask if we're dealing with a stable gas, then the first question is that gas water soluble? And if or is it fully oxidized? So an example of this would be something like SO3. And the question is basically, is it water soluble? If it is, then that's fine. It's going to just get returned to the Earth's surface via rain. So it'll get incorporated into rain, into clouds, and then and rained out of the troposphere. If it's not, then we kind of proceed and just ask, well, is it a molecule that absorbs light such that it would undergo some kind of photochemical reaction where we'll dissociate in some way? If the answer to that is yes, and we'll see an example of this, if the answer to that is yes, then what we go to is we do that photochemical reaction, we produce the radicals, and then we go look at a different flowchart in terms of how those radicals will behave. If the answer is no, then we ask, if the answer is no, then we ask, well, does the molecule have multiple bonds so that OH could add to it, so that hydroxy radical could add to it? If the answer to that is yes, then we essentially react. Then the primary reaction that's going to occur is hydroxy radical adding to it, and then we kind of go on from there. If the answer is no, then we ask, does it have a hydrogen that could be abstracted by hydroxy radical? And if the answer to that is yes, then we do hydrogen atom abstraction, and we go from there. And if not, then we essentially just say this gas has no tropospheric sink and is going to end up in the stratosphere, and that's where things like CFC is. So, all right, that maybe that makes some sense, but I'll go through an example of this. So then what about once we get to radicals, though? What happens there? Well, we have a different flow chart for that. And we just kind of ask, well, first off, do I have a peroxy radical or a peroxy bond? And what I mean by that is some generic OO radical here, or it could be HOO. It's essentially, or I guess it's essentially just some oxygen-oxygen bond where the one oxygen on the end just has a radical on it. That's a peroxy bond. If the answer to that is yes, then it's going to react with nitric oxide, or NO. Then NO is going to come in and will abstract one of those oxygens off to form NO2. And then you'll be left with, you're basically just plopping one of the oxygens off, and you're left with whatever was left over, just with that oxygen having a radical on it. If the answer to that is no, then you keep kind of going through and ask, well, does it have an oxygen-centered radical, like shown here? Does it have an oxygen-centered radical that is on a carbon that is attached to another carbon? And it doesn't have to have two hydrogens here. One of these can be an R group. And if you're unfamiliar with what R means, it just means R is just a placeholder for other carbon stuff. it could be any kind of carbon group. That it could be one carbon or it could be 100 carbons there. It's just, that's kind of just carbon with then other hydrogens and stuff attached to it. And then if it does, then you can have a scission reaction occur where this, if I draw this out here, it's actually, carbon, carbon, hydrogen. Let's draw hydrogen there and oxygen radical. Well, this radical will come to form a double bond, but it needs one other electron to form the double bond, right? So that will come actually from this bond. One of the electrons from here will come and form the double bond, and that breaks this bond. So that carbon-carbon bond gets broken, and you end up forming a carbon-oxygen double bond, as I've sort of drawn there. If you don't have that, then you keep going and ask, well, is there a hydrogen that you could remove such that you would form a double bond or a triple bond? And if you do, then oxygen will come in and take off that hydrogen. And if none of those are true, then oxygen just adds to the radical. It might seem like a lot, so maybe that doesn't seem more helpful than what we had before when we were trying to distinguish this, but let's go through a specific example of this. So let's look at the just tropospheric oxidation of methane. So methane, main component of natural gas, just CH4, it's the simplest hydrocarbon, and it is mostly oxidized in the troposphere, but since there's a lot of it and the initial reaction is slow, some of methane actually does escape up into the stratosphere. But this is probably our simplest oxidation process. So the very first thing, we're starting with CH4 here, and the first thing we note in terms of distinguishing which flowchart we need to use, we're starting at a stable species, so we're going to start with our neutral species flowchart first, and just ask, well, is my gas water soluble? You might not know off the top of your head, but you have to reach back to Gen Chem to concepts of polarity and things like that. CH4 is a non-polar molecule, water's polar. CH4 methane's not really water soluble at all, so we keep going to the next one. Does it decompose in sunlight? Well, this one you wouldn't know off the top of your head, but I'll just tell you it doesn't. It doesn't really absorb in the visible region or even in the UV that much. So nope, we don't have any of that. So then, does it have multiple bonds that OH can add to? Nope, there's no multiple bonds. It's all just C and H bonds. So then, does it have a hydrogen that OH can abstract? Yes. This is where we stop. So the first reaction then is OH radical comes in, hydroxy radical comes in, abstracts off a hydrogen from H2O, and you're left with CH3, where there's now that radical is on carbon. So remember that double bond is 2 electrons, so if we take off a hydrogen with its electron, we're left with just 1 electron, so that's now an unpaired electron on carbon. Now we just reevaluate the situation and say, so where are we at? So we're now at a radical species. So I'm going to flip over to my other flow chart and say, does it have a peroxy bond? Well, that would be an oxygen-oxygen radical. No, it doesn't have any of that. So no to the first question. Is it some kind of type where it's got an oxygen-centered radical? No. Can you remove a hydrogen such to form a double bond to oxygen or a triple bond? No, no. There's no oxygens involved. We just go all the way down to the bottom. O2 adds to the radical. So that would be the next step here. O2 comes in and simply adds to that radical to form a new radical that's now oxygen-centered. We stick on this flow chart because we're still at a radical species here. And this will still tell us how we kind of proceed. So we've got now we look at this and we start at the top. Do we have a peroxy bond? Yes, now we do. CH3, it's COO radical, that's a peroxy bond. So that will undergo reaction with nitric oxide, or NO, to oxidize it. Just basically nitric oxide comes in, plucks off one of those oxygen atoms to go to NO2, and then you're just left with, now you're just left with a carbon-oxygen single bond now with a radical on that remaining oxygen. We keeping track of, I'm sorry, I'm moving kind of quickly, but are we Is that tracking okay, more or less? Making some sense? Okay. Stop me with questions if you got some. So, all right, we're still on our chart then. So we essentially go, now it might help if I actually drew this out. So what this looks like is C, H, 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 O, and then radical there. I guess I can draw out the other lone pairs on oxygen. Maybe that would be helpful. I don't know. Maybe I should have the radical right here, but I don't. But now if we kind of walk through, we don't have a peroxy bond. We don't have multiple bonds. We don't have a carbon-carbon bond at all because we only have one carbon. So that's not. Can H removal from this result in a double bond? Well, actually here we could. So I've got a hydrogen on, I've got hydrogens on carbon. If I came in and let's see here, if I come in and pull off one of these hydrogens, let's just say this one, and take its electron with it, I'll have one electron here. If that one electron comes to form a bond there, or comes here and combines with the one electron from the oxygen, that'll give me two electrons. Ooh, not sure what's going on there. There we go. Now I'll have two electrons there, so that'll form that second bond, and that will get me then to, you know, H, C, H, double bond O. And that's definitely favorable. I traded in a CH bond for a carbon-oxygen double bond. So that's essentially just my next step. And I get to now what's known as formaldehyde. So I've gone from methane to formaldehyde through this series of steps. This is why I hate lecturing like this. It's so boring. All I do is talk all the time. You just need something entertaining. Don't worry, I'll put you to work here in just a moment. But is all of this making sense so far? We tracking okay, more or less? All right. I'm going to take your silence as approval. So, all right. So now what we're not all the way done though. So if we remember back to our short lecture on oxidation states, the carbon here is not fully oxidized. If I look at the carbon in formaldehyde, right? If oxygen is -2 and each of the hydrogens is +2, carbon's just 0 right now, but it can be oxidized all the way up to +4. So here, essentially, what I'll have is now I'm back at a stable species. There's no radical at all. So I have to flip back to chart number 1 to decide what's going to go on from here. And I'm just going to keep doing this until I get to the point where I don't do any more oxidation reactions. So if I'm here and, okay, is formaldehyde water soluble? Actually, formaldehyde is water soluble, so some of it can be removed in that process. But if we're considering how it might react further, we'll just keep going. And does the gas photodecompose in sunlight? Well, actually, yes. This is not one that you would know, but aldehydes, and I'm assuming that most of you have not taken organic chemistry, so you may not be familiar with the term aldehyde in terms of what it means. But an aldehyde is simply when I have a carbon-oxygen double bond and then there is a hydrogen attached to that carbon. R just symbolizes any other carbon group, or it could be a hydrogen, any other carbon or hydrogen group here. So that's the general structure for aldehydes. Aldehydes do tend to absorb in the UVA region, and they will undergo a photochemical reaction where you cleave the carbon-hydrogen bond. It tends to be a bit weaker than it normally is under these particular circumstances. And so you cleave that, and that leads you, literally, you just chop this in half, essentially, and you give one electron one way, so you get H dot, and you put the other electron the other way, and that gives you, it's misleading the way it's drawn here. It's not on oxygen. It's a carbon-centered radical right there. And then that H dot that's left there, we could follow through our second chart here and just say, you know, what happens with that? Well, that's just going to add that. If we follow through the chart, that's just going to get down to the bottom here, and O2 adds to it. So we get the hydroperoxy radical, which we should remember that just then reacts with nitric oxide to generate NO2 and then hydroxyl radical again. So now we've regenerated the hydroxyl radical that we started with, that we started this whole sequence off with, because if this reacts with NO, you get OH radical plus NO2. So now we've regenerated the hydroxyl radical that we started with. And then from here, we've got a carbon-centered radical. It doesn't have a proxy bond. It only has one carbon. But we could remove, in this case, let's see here real quickly. What do I have here? I don't think I can remove a hydrogen. Well, yes, I can, actually. In this case, what I can do is remove a hydrogen here to essentially, if I remove the hydrogen on carbon, it will allow me to get to a triple bond, essentially. Drawing the electrons is slightly, is maybe a little bit weird, but essentially just, I don't have a lone pair on carbon right at the moment. I've got 2 lone pairs on oxygen. If I take off this hydrogen, so if I just cleave it and I leave 1 electron left over, then carbon's actually only going to have 6 electrons, 2 from there, 4 and 6 from the double bond. So one of these lone pairs can come in and form a triple bond, and you get to carbon monoxide. So now and notice what we did, we made another equivalent of hydroperoxy radical, which then goes on and reacts with NO to generate OH radical plus NO2. Notice that now we've generated more hydroxy radical than we started with, so it's not just a catalyst, it's also a product of the reaction, which means that if we have a bunch of this, if we dump a bunch of methane into the atmosphere, we have a net increase in the amount of hydroxyl radicals that are present in the air because it's a product of this reaction. All right, we'll get to CO, and I'm just going to speed forward. So now we're back to CO. We're actually back to the previous chart. We're at a stable species again, no radicals there. But what we can see is that essentially if we follow through that, OH can add to it. We have a multiple bond. We've got triple bond there. OH hydroxy radical can add to that to generate, HOC. Now we've broken that triple bond back to a double bond now. And then from here, now the last step, so now we're back at a radical. Does it have a peroxy bond? No. It doesn't have 2 carbons? No. But can we remove a hydrogen to make a multiple bond? Yes, we can, because if I come in and remove this hydrogen here, if I chop this, the 1 electron that's left over goes to combine with that one to form a multiple bond. And so O2 comes in, pulls off a hydrogen, and gets me to CO2. Plus another equivalent, essentially, of hydroxyl radical and more oxidation of NO. Do we track with that okay? More or less? Hopefully it was a little bit more helpful than what we did on Wednesday, or maybe it helps explain it a little bit more. All right, I have talked for about 20 minutes, and that is way too long. So it's your turn. Let's take about 2 minutes and talk to, turn around to the person somewhere in the approximate 6-foot radius of you. And I've thrown the flowcharts up there, which hopefully you can read at that distance. I apologize if it's a little bit small. I've got both of those. And I've got 3 molecules up there. So turn to a partner or 2 sets of, or a group of 3, and let's just discuss really quickly what mode of reactivity are we going to get from each of these? What's going to happen? What's the next step for any of these intermediates, or for any of these species? What's going to happen next? And just as a heads up, ethylene here in the middle, if you're working through the chart over here, it does not decompose in sunlight. So that should help. All right, go ahead and turn, and let's get a little bit of discussion going here. All right, how are we doing? Do we at least have an idea for a couple of these? You think? Maybe? Okay, we're a little shaky. In the interest of time, we got to sort of keep going. So since this, actually, this isn't the main thing that I want to talk about today. So let's just really quickly, though, well, I'll just sort of review this real quick. So this first one here, what we're looking at is, first off, we got to just choose the right flow chart. So it is a radical, so I want to start with the flow chart on the right. And here, does it have a peroxy bond? Well, yes, actually, that is what is going on right here. So OO radical, that's your peroxy bond. So yes, so what I would expect to happen is I would expect NO to come in and essentially just chop off that hydrogen there. That's essentially what is going on there. So let me just real quickly check. I know there's a bunch of messages on. Okay, yep. So that's what's going on for that first one. For the second one, where you don't have a radical, so we choose the flowchart on the left. Work through, is it water soluble? I didn't tell you, but it's all carbon and hydrogen bonds, so it should be non-polar. So it shouldn't be water soluble, and it's not. So I don't have to worry about that. I did tell you that it doesn't photodecompose, so that we don't have to worry about that. So then the next question is, does it have multiple bonds? And the answer to that one is yes. So what we would expect to happen here is to have OH radical come and essentially add to this, which the resulting product from that is going to be carbon, carbon, hydrogen, hydrogen. I'm just going to have a radical here, carbon, H, H, and then OH. If you're confused why that happens, well, this carbon here that you're adding to already has 8 electrons around it. So if you bring in another electron and try to form a bond, well, one thing, you got to bring an electron from somewhere in order to make that bond, because you need to have 2 electrons in a bond. So that electron comes from this double bond. So that's where the other electron from that bond comes from. But that leaves then 1 electron left that used to be in the double bond. That goes and sits on the other carbon, essentially. So that's how we got to there. And then this last one, we're starting with a radical, so we got to start on the right-hand flow chart. It doesn't have a peroxy bond. Here, it doesn't have carbon-carbon bonds. So then we get down to, can H removal convert a single bond into a double bond? Because it's the formation of that double bond that's favorable that drives that to happen. And here, yeah, we could actually. If we pull off the hydrogen here, so if I chop this off, that would leave me 1 electron and 1 electron there. I could bring that in to form a double bond here, and I would get sulfur trioxide, which is just, if you're concerned about the octet rule, just remember that sulfur, anything in row 3 or greater is allowed to break the octet rule. Sulfur, phosphorus, chlorine, those are allowed to break the octet rule. And we do break the octet rule primarily in order to satisfy formal charge things, so another Gen Chem 1 topic. But that's here, this would get us a sulfur-oxygen double bond, so that would work. All that, does that make some sense? Oh dear. Oh, sorry. You thought we were going, after you did that, I wanted you to take it all the way to CO2. Oh dear. Well, that would take a while. Well, we will do that, but I didn't mean for you to have to do that. So hopefully that helps. Any questions on any of that? Check the Zoom chat. Okay. Looks like just some conversation there. So. Okay. Well, I've got about 20 minutes left. So if we're doing okay, bear with me while I speed into kind of the next topic and what's supposed to be the main topic for today. So, and that's photochemical smog. So if you think smog and the first thing that comes to your mind is this, that's the first thing that comes to my mind, but that's not what we're talking about. So, and if there's anybody out there who's really confused and has no idea what this is, go watch The Hobbit or something like that. It's not nearly as good as The Lord of the Rings, but it's still worth watching. So this is what we're actually talking about. Smog is actually kind of a portmanteau of smoke and fog, coined in the early 1900s. Is essentially just we have this really awfully yucky looking atmosphere, primarily in major cities. And there's a number of factors that go into that. And it kind of obscures vision. As you can see, this is just 2 different days from a city in China. And you can certainly see the difference in air quality. And the primary, I guess the primary factors that we're concerned about in smog, or the primary things that make it up, are ozone. Then there's NOx species, which is just a variety of, I'll go through what that is. There's SOx species, and then there's VOCs. So what in the world is all of that? Well, first off, ozone, we know what that is. The problem is it's not in the right place. It's great when it's in the ozone layer because nobody breathes it, but it's toxic. It's and leads to a number of health issues. So you don't want to breathe it because it's pretty reactive. But so in that case, smog is sometimes referred to as like an ozone layer in the wrong place. That's one of the major concerns. NOx, that's sort of a placeholder for a bunch of different nitrogen oxides. So a couple here are listed: nitric oxide, we've seen that before, nitrogen dioxide, nitric acid, that's another one here. There's others, there's actually a bunch of other ones as well. One thing here to note with NOx is nitrogen dioxide is actually a brown gas. We've already seen it kind of absorbs in the visible region a little bit. And so this picture here isn't really showing it just because there's so little light that's actually getting through. But if you've ever flown into like Los Angeles or something like that and the air all looks brown, this is why it looks brown, is because of the nitrogen dioxide that's in the air. So that's one component there. The SOx species, that's kind of a number of just sulfur or oxygen species, so sulfur dioxide, sulfur trioxide, and then sulfuric acid. And you can also imagine that you probably don't want to be breathing either nitric acid or sulfuric acid, although you certainly are on days when the air quality is particularly bad. And the last component here is VOCs. Those are volatile organic compounds. The definition for this, so a couple things. Organic compounds with boiling points between 50 and 260 degrees C. That sounds like quite a bit of a range. But when we talk about what kind of source of emissions for those, it might make a little bit more sense why we go all the way up to 260. The other thing here is what is meant by an organic compound. I'm assuming, I don't want to assume, let's see. All right, for those people who are physically here, has anyone taken organic chemistry? No, okay. Not surprising. I wouldn't expect you to as environmental engineers. It's not required. Essentially, organic just means it contains carbon. So it has to contain carbon in some form. And primarily, often will also contain hydrogen. So a lot of these are hydrocarbons, but maybe not all of them, but most of them will be. Examples of, just random everyday things that are volatile organic compounds. Gasoline. If you ever fill up your lawnmower like I do and you're not very good at it, you spill gasoline, and that, then evaporates pretty quickly because actually gasoline's boiling point's pretty low. It's like probably only, I have to remember here, octane 50s or 60s maybe for its boiling point. But then fingernail polish remover, that's acetone. That's something some of you use. I don't, but some of you probably do. And air freshener, things like Febreze, that's another source of these. There's any kind of odorant or deodorant, any kind of aromatic kind of scent. Those are all generally hydrocarbon species that could be emitted. And in terms of, this isn't a great graph, I'll sort of skip through it quickly, but basically if you want to know some numbers, this is from your text, about 16.7 million tons of VOCs that are emitted every year. And this is about 15 years old, so I don't know what the actual numbers are today. I should look those up, but this is from your text. And you can see a bunch of that comes from from vehicle emissions. So when you burn gas in your car, a bunch of the times, not all of it gets actually burned. Some of it just gets emitted as the volatile, as the vapor form. Then we've got, of course, off-road vehicles, solvents. This is more in, I guess, trying to think here. This is probably more in industrial examples, but that's things like nail polish remover and paint thinners and all that. All right, so where does all of this come to then? So if we've got all of these components in photochemical smog, you might have a few questions. And it might be helpful to look at our kind of cycle of reactions that we had earlier. Don't worry about trying to write this all down. But last time when we'd sort of gone over this kind of overall cycle of where hydroxyl radical initiates the, so if we started, here, something hydroxyl radical kind of initiates the oxidation process for all of the different compounds. Here I just use carbon monoxide as an example, but I can replace that with VOCs in this case. So that's where they kind of play into this cycle here. And generally we get either abstraction or addition, and we'll come out with some intermediate here, and then O2 comes in, and we end up generating hydroperoxy radical, and then some other species here, and eventually CO2. So when I look at this in terms of air quality and photochemical smog, where that comes from, well, VOCs and nitric oxide are the two main inputs. So when you wake up in the morning in a large city and traffic, you get into rush hour, the cars are primarily emitting an awful lot of nitric oxide and all of these forms of hydrocarbons, whether they're partially oxidized or completely unoxidized. And then as all the businesses kind of, well, you're getting generation of these two. These are the two primary inputs. Now, the primary outputs that we worry about are ozone, which comes out of here, nitrogen dioxide, and then the products of the VOC emission or a VOC oxidation. So some of these are aldehydes, we get to carbon monoxide, and eventually we get to CO2. But I'll sort of walk through some of that. Now, there's a couple other things to note here. So O3, ozone, NO2, and then partially oxidized VOCs are the primary causes of concern and the primary causes of that ozone, of that photochemical, of that smog. We'll talk about why it's called photochemical smog in a moment. But it's primarily ozone that's the problem, NO2, both of those contribute to that kind of white or brown haze. And then also the partially oxidized compounds that result from those hydrocarbon oxidation, that all contributes. A couple other reactions we should note. One is that actually the ozone concentration is related to the nitric oxide concentration, because if nitric oxide is too high, basically as long as this is high, then we actually won't have a ton of ozone because it gets destroyed in this reaction, but that generates more NO2. Other things, if the radical concentration is high in the air, you can get radical combination between nitrogen dioxide and hydroxyl radical to generate nitric acid. That's a problem because then that becomes a component of that air and you breathe that. And then the other thing is that if the radical concentration is also high, you can also get reaction, you can get combination between nitric oxide and hydroxyl radical to form nitrous acid. And this during the day is normally photolyzed to generate NO and hydroxyl radical again, but at night this concentration builds up. All right, bear with me. I know I hope you're not bored, but bear with me as I kind of, where do some of these things come from and what's the overall result? Well, one question might be, where does NO come from? We get emission of hydrocarbons. If you spill gasoline or something like that, that evaporates, that goes, where does NO come from? Well, NO actually comes from this reaction between nitrogen gas and oxygen gas. And if you think this looks weird, It is a little bit because it's uphill by 182 kilojoules per mole. So this is very endothermic and doesn't happen at room temperature at all, because it looks something like this. We've got two reactions. First, you've got to cleave O2 to generate individual oxygen atoms. And that takes a bunch of energy. And then that O, that single oxygen atom, I've only drawn one of them there, but you split O2 into two of those. That then has to react with N2 to form essentially, oh, wow. Sorry. I think I've got this, obviously, if you look at that, one N or one oxygen and two nitrogen atoms forms N2O, not NO2. But so sorry for the misdrawing here. It's likely that you've got nitrogen atom that splits and you have to react that with oxygen, or you have to react this oxygen a couple times. But so my apologies, I've got that messed up here. But bear with me, consider that the point is still valid even if I've drawn the specific reaction incorrectly. Essentially, what we end up with is that, no, I have not drawn the specific reaction incorrectly. I apologize. Still, brain's not working for some reason. It's just that I have up here where my cursor is, that should be a nitrogen, not an oxygen. That's what I've confused myself on. So now you end up abstracting, you basically end up forming NO and then a free nitrogen atom. These are both super high in energy with really high activation energy barriers. So it doesn't happen at room temperature, but in the combustion engine of a car, so here you can see the activation energy barrier for that last reaction is 314 kilojoules per mole. In the combustion engine of a car, or in the combustion reactions for electric power generation, you get to extremely hot temperatures, sometimes all the way up above 2,000 degrees Celsius. That doesn't change the activation energy barrier, but it does change the energy of the reactants and the energy of the intermediates. So if you've just got more thermal energy, then your overall energy is just at a higher value, which means then that essentially your barrier is decreased, not because you lowered the energy you needed to get over it, but because you raised the energy of the starting materials and the intermediates. And so at high temperatures, this reaction will actually proceed even though it's endothermic, because you have enough energy that your activation barrier gets low, that your overall activation barrier is essentially reduced. And so you'll produce NO in this process, but then once you cool back down again, even though NO is definitely less stable, like NO is definitely significantly higher in energy than O2 and N2, it's frozen as NO because the reverse reaction, the activation barrier is too high. And so once you've cooled it, the reaction's irreversible, even though it was net endothermic. All right, so primary culprits here for NO generation are cars and electric power plants, both of which are basically just doing a lot of combustion reactions. Again, I'm going to skip through this quickly, but basically we generate an awful lot of NO every year. So I'll skip through that really quickly, just in the interest of time. And get to the second question, which is so all right, that's where NO emissions come from. So that was the whole point of that, was where are we getting the NO input? The second question is, why is VOC, why is that really an issue if it ends up getting oxidized all the way to CO2? CO2 is not a problem, right? We breathe that out all the time. Why are these a problem in smog? Well, here's just an example that we'll go through quickly. So we've got, if we take something like this, it's a alkene, a carbon-carbon bond. This is a double bond. This is something that could be an output from fossil fuel, something output from your car, partially oxidized species. If we follow our chart, we're going to react with this with hydroxyl radical to get the reaction started. And you just do addition. This is something we actually saw in that first problem. And then after that, if you follow through the chart with the radical there, we're going to get oxygen addition to that. And then we have a peroxy radical. So that undergoes reaction with nitric oxide to cleave off this one oxygen atom and leave you just with the other one. At this point, if you follow down through the chart, we'll see that we have a carbon-carbon bond that could be split in this particular example. So we end up doing that. We actually draw this, apologize, this comes down, we break that single bond, and then the one electron just goes back onto the carbon, and we end up with an aldehyde right here, and then a new radical. And that new radical, if we follow through our flow chart, that can get oxidated. We just can pull off a hydrogen from that to generate another equivalent of aldehyde. And if I keep in mind that the hydroperoxy radical that I form here reacts with nitric oxide to generate NO and a hydroxyl radical, I'll notice that I have regenerated the hydroxyl radical, that I started with there, so that ends up canceling out. I react a couple equivalents of NO from here, and I've generated a couple equivalents of NO2. So if I add everything up, what I see is that one reason, now I'm not done with the oxidation of the compound yet because I'm at an intermediate stage. I'm not at CO2 yet. But one reason this is partially a problem is that this, the oxidation process generates a bunch of nitrogen dioxide. So that then is a main contributor in photochemical smog. From here, all right, before I speed through in the next couple minutes, are we tracking okay with that? More or less? I know some hefty writing. Again, I will post all of this, so. All right, so from here then, we're not quite done. We have to finish oxidizing that aldehyde, and we'll see why that's also an issue. Because, the overall point here just being that you increase in NO2, and then that also leads to an increase in nitric acid as well. And so that's another contributor to the smog. The second part is, okay, let's finish with the oxidation of the aldehydes. There's actually two pathways for that. The one is the main one, which is just photochemical decomposition. We said that aldehydes do absorb UV light. So you break this, essentially you split off the R group, or you could split off the hydrogen group as well. But you split this off, that increases that decomposition. If you produced a whole bunch of aldehydes and then you get photochemical dissociation, now you have a ton of free radicals in the air, which then is also a contributor to health problems, because those will not only react right here, but if you breathe them in, then they'll react with you. And the oxidation of each of these just results in a bunch of, so here we've got essentially the abstraction of a hydrogen to generate carbon monoxide, and then that just gets oxidized the way we did before, up to CO2. I've highlighted that we generate two equivalents of hydroperoxy radical here, because that's going to then, both of those equivalents are going to lead to a net increase in NO2, essentially. That R radical also reacts with O2 to generate a peroxy radical that then gets oxidized. All of this, we're just generating a bunch of hydroperoxy radical, which then generates a bunch of hydroxyl radical and NO2. So we're basically just driving up the NO2 concentration. Bear with me for the -1 second that I have left. The other thing that happens here is that we can get H atom abstraction to generate essentially just a carbon-centered radical here. And that carbon-centered radical can undergo addition with oxygen. And then at this point here, if the radical concentrations are high enough, then, and I promise this is the last bit, then you can actually get combination, right? You've been pumping out NO2 as the end of this process. Eventually, you get some of these aldehydes, and you add to this and form this kind of peroxy species. But rather than oxidizing it by rather than reacting with NO to cleave that oxygen-oxygen bond, if you've got enough NO2, you'll actually get combination, and that forms peroxyacetyl nitrate, which is a potent eye irritant. So that's another major factor in smog as well, another health contributor. I'm going to stop there. Sorry I went over, and I'll let you guys go, and we'll maybe pick up with some of this and hopefully finish chapter 3 on Monday or Wednesday of next week. Sorry for running kind of long.